This is SpaceTime Series 22, Episode 5. Coming up on SpaceTime, discovery of a second repeating fast radio burst, searching for the Sun's siblings, and rapid starbirth detected in the Magellanic Clouds. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have discovered another mysterious fast radio burst signal which appears to be repeating. It's only the second time ever that a repeating fast radio burst has been detected. The findings, reported in the journal Nature, will help astronomers move a step closer to working out what's causing these extremely powerful yet incredibly short energy bursts which originate from the distant universe and last just a nanosecond. Around 60 fast radio bursts have so far been detected, and almost all have been single events, bursting just once and then never again. These short ephemeral qualities have made fast radio bursts one of the biggest mysteries in astronomy today. That's led astronomers to suggest that they could be generated by some sort of cataclysmic event, such as, for example, a star destroying itself in a supernova explosion. Prior to this new discovery, only one other repeating fast radio burst had ever been detected. That was a discovery made by the Arecibo radio telescope in Puerto Rico in 2015. Now, the detection of a second repeating fast radio burst suggests there could be more than one way to generate these events. The leading hypothesis now is that fast radio bursts could be generated by some kinds of stars being consumed by black holes. The discovery of this second fast radio burst repeater was made by CHIME, the Canadian Hydrogen Intensity Mapping Experiment, a new radio telescope in British Columbia being operated by a collaboration from the University of British Columbia, McGill University, the University of Toronto, the Perimeter Institute of Theoretical Physics, and the National Research Council of Canada. The repeating fast radio burst was one of 13 FRBs detected over a 3-week period during CHIME's pre-commissioning phase, while it was running at only a fraction of its full capacity. One of the study's authors, Ingrid Stairs from the University of British Columbia, says the discovery of a second repeating fast radio burst suggests there are probably more out there. And with more repeaters and consequently more sources available for study, astronomers may be able to understand a little bit more about these cosmic puzzles, where they come from, and maybe even what's causing them. Before CHIME began to gather data, some scientists wondered if the range of radio frequencies the telescope was designed to detect would be too low to pick up fast radio bursts. You see, most of the fast radio bursts previously detected have been found at frequencies near the 1400 MHz range. That's well above the new Canadian telescope's range of 400 to 800 MHz. But these first CHIME results have certainly settled those doubts, with the majority of the 13 bursts being recorded well down to the lowest frequencies in the CHIME range. In fact, in some cases, the signal at the lower end of the band was so bright that it seems likely that some fast radio bursts will be detected at frequencies even lower than CHIME's minimum of 400 MHz. The majority of these 13 fast radio bursts detected are showing signs of scattering, a phenomenon revealing information about the environment surrounding the source of these radio waves. In fact, the amount of scattering observed by CHIME has led the authors to conclude that the sources for these fast radio bursts are powerful astrophysical objects, more likely to be locations with special characteristics. That could mean it's in some sort of dense clump like a supernova remnant, or near the supermassive black holes at the centers of galaxies. Ever since the very first fast radio bursts were detected, scientists have been piecing together the signal's observed characteristics, trying to come up with models that could explain the sources of these mysterious events and provide some idea as to the environments they occur in. CHIME's detections at lower frequencies mean many of these theories will now need to be reconsidered. That's because some of these hypotheses have involved sources that simply can't produce anything below a certain frequency, and so they can now be ruled out. Kendrick Smith and Dustin Lang are two of the study's authors.
I would say that once a decade or so, astronomers discover a new type of mysterious event. For example, in the history of astronomy, pulsars were an unexpected mystery, gamma ray bursts were a mysterious surprise, and so on. And the 21st century mysterious surprise is the fast radio burst, which is some sort of very energetic event that happens at a great distance that we observe here on Earth as a brief pulse of radio waves coming from very far away.
Fast radio bursts are a really exciting mystery. We basically don't. We have more ideas of what they could be than we have actual detected fast radio bursts. So the CHIME telescope doesn't look like you might expect a telescope to look like. The physical telescope has no moving parts. It has these cylinders that are 20 meters wide and 100 meters long, so the collecting area is huge. That's one of the great benefits we have.
The cylindrical design of CHIME means that we see a stripe on the sky, and as the Earth rotates, that stripe sweeps out the whole sky every 24 hours. I think we're doing something really new with CHIME, which is figuring out how to scale the computations that are needed to do radio astronomy up to unprecedented volume. The fast radio burst search that we wrote here at Perimeter Institute is something like a few hundred times larger than the searches that have been done to date. We have, for example, the highest discovery rate for fast radio bursts of any telescope, but we get it by generating an avalanche of data. We have about 100 times more data than a typical radio telescope, and the computational challenges are immense.
So this was a huge challenge, and one that hasn't really been attempted before, a real-time streaming fast radio burst detection system. And so it's really a pathfinder or a leader in this area. In the CHIME fast radio burst system, we look at every bit of data once, and a second later it's gone. So building this system was a real challenge and a real different sort of software beast.
Throughout the first few weeks of our FRB search, we were finding fast radio bursts at the rate of one FRB every 2 days or so. That's actually a really impressive number, since the total number that were ever found since the initial discovery in 2007 is around 50. In the first few weeks of our search, we found a new repeating FRB. Prior to that, the situation was that about 50 fast radio bursts had been observed, ever. And one of them was a repeating fast radio burst. The other 49 had not been observed to repeat, despite a lot of telescope time spent looking, and that was a real mystery. So what we've shown is, by discovering a second FRB, is that the repeating FRB is not unique, and maybe we can hope to find more.
So with these two new papers, what the CHIME Fast Radio Burst collaboration has shown is that, well, a few things. The CHIME FRB instrument works, and we're finding fast radio bursts. The 13 we report in this paper were found during our kind of pre-commissioning phase, when we were basically turning the system on for the first time and determining whether it worked or not.
It's very interesting that it really is one of the most powerful radio telescopes in the world, and we've made it work through new software and new computing techniques that were really developed here in Canada for the project. And so it's very exciting that Canada is really leading the world in this particular part of astronomy.
That's Perimeter faculty member Kendrick Smith and computational scientist Dustin Lang, explaining how the CHIME radio telescope zeroed in on its collection of newly discovered fast radio bursts. And this is SpaceTime. I'm Stuart Gary. A new study searching for the Sun's siblings has revealed the chemical DNA of more than 340,000 stars in our Milky Way galaxy. The findings by the Galactic Archaeology with Hermes, or GALAR survey, is part of an ambitious project using the Anglo-Australian Telescope's Hermes spectrograph to obtain the chemical composition of well over 1 million stars in our galaxy. Put simply, GALAR aims to understand how the Milky Way galaxy was formed and evolved. Astronomers know that galaxies grow by merging with or cannibalizing other galaxies. In fact, the Milky Way is doing that right now. Not only is it cannibalizing the Sagittarius dwarf galaxy on the far side of the Milky Way, but it's also starting to drag both stars and gas off the nearby Large and Small Magellanic clouds. GALAR is studying the composition of stars in the Milky Way's galactic disk to determine which stars originated in our galaxy and which came from other galaxies, ones that have been cannibalized by the Milky Way over the past 12 billion years. The survey will also try to determine exactly what's been driving major episodes of star formation in the galaxy's disk. And it will search for stars with the same chemical composition as the Sun. That means solar siblings, stars born in the same molecular gas and dust cloud as our Sun. To do all this, Galia uses the Hermes spectrograph attached to the 3.9-metre Anglo-Australian telescope at the Siding Spring Observatory in far western New South Wales. Spectrographs work by splitting light into different wavelengths using something like a prism or a diffraction grating. When electromagnetic radiation, such as visible light, is emitted by an object, or when it passes through gas, it produces spectral lines at very specific wavelengths. These wavelengths correspond to specific elements or molecules, letting scientists know the chemical composition of the gas. Absorption lines appear as dark lines superimposed on a rainbow continuum. They're caused by an atom or molecule in the gas absorbing a photon with enough energy to move an electron to a higher energy level. On the other hand, emission lines appear as discrete coloured lines, usually on a black background. These emission lines are caused by electrons of an excited atom or molecule moving between different energy levels as it returns down towards a ground state. Tests in laboratories have provided scientists with a list of spectral signatures of all the known elements and most of the molecules and ions. So, by comparing observed spectral signatures with those on the list, astronomers can determine the exact chemical composition of distant stars simply by looking at their light. It's an amazing tool, and it doesn't end there. They can also tell if the object being observed is moving towards or away from them, simply by whether the spectra is being Doppler shifted away from its usual position and more towards either the blue or red end of the spectrum. Now, if the spectra is blue shifted, it means the emitter is moving towards the observer. On the other hand, if it's red shifted, it means the emitter is moving away from the observer. The degree of that shift tells you how fast the object or emitter is moving towards or away from you. And like late-night shopping on TV, there's still more. The spectral lines can also be broadened or narrowed depending on the temperature of the object or emitter, or through interactions with neighbouring atoms, ions and molecules. The spectra being collected by Hermes traces the ancestry of stars by showing astronomers their chemical composition. One of the scientists behind the Galia project, Dr. Gavandi De Silva from the University of Sydney, says no other survey has been able to measure as many elements for as many stars as Galia. This data will enable such discoveries as the original star clusters in the galaxy, including the cluster which gave birth to our Sun and its siblings. You see, like all stars, our Sun was born as part of a cluster containing thousands or maybe even millions of stars deep inside a gravitationally collapsing molecular gas and dust cloud. Every star in that cluster will have the same identical chemical composition or DNA. Once stars form and begin to radiate heat and produce stellar winds, they often quickly move away from each other and are moved further apart by the Milky Way's rotation and gravitational influences from other clusters over billions of years, causing them to be scattered all across the sky. The Galia team hopes to make DNA matches between stars to find their long-lost sisters and brothers. For each star, the DNA the team are looking for is the amount and proportions of roughly 24 specific chemical elements they contain, such as oxygen, aluminum and iron. The light from the star is collected by the telescope and then passed through the Hermes spectrograph, which splits it into its detailed rainbows or spectra. Astronomers then measure the locations and sizes of lines in the spectra to work out the amount of each element in the star. But collecting the data is painstaking. The Galia team have spent more than 280 nights at the telescope collecting the spectra, and it takes an hour to collect enough photons of light from each star to obtain a spectra. The good news is they can observe 360 stars at a time using Galia's fibre optics. The Galia survey was conceived more than a decade ago as a way to unravel the history of the Milky Way, and the Anglo-Australian Telescope's Hermes instrument was specifically designed and built for the Galia survey. Measuring the abundance of each chemical in so many stars is an enormous challenge. To do this, the Galia team have developed sophisticated analysis techniques. This involved training the instrument to recognize patterns in a spectra of a subset of stars which have been analyzed carefully, and then use machine learning algorithms to determine the exact amount of each element for each of the 340,000 stars being surveyed. The release of the Galia survey data has been specially timed to coincide with the release of data from the European Gaia mission. The Gaia satellite has mapped more than 1.6 billion stars in the Milky Way, making it by far the biggest and most accurate atlas of the night sky to date. In combination with the velocities from Gaia, Gaia will give not just the positions and distances of the stars, but also their proper motions within the galaxy. In fact, De Silva says the accuracy of the velocities being achieved with GALAR are unprecedented for such a large survey, allowing astronomers to get a very detailed understanding of the history of our Milky Way galaxy.
We are aiming for 1 million stars as a large final goal. So 340,000 is where we are up to at the moment.
Have you reached the point yet where you're starting to compare spectral signatures to try and find siblings of the Sun?
Yes, so with this data, what we can do is try and identify the star clusters that were formed at the early stages of formation of our galaxy. So one of those star clusters will be the cluster where the Sun was formed. So finding that cluster will give us an idea of where other stars that were formed together with the Sun in the same cluster. So those stellar siblings, if you like.
I remember way back, and I think it was about February 2014, I wrote a story for Star Stuff, the predecessor to this program, SpaceTime, and that covered a report in the Astrophysical Journal about a star called HD 162826. About 110 light years away in the constellation Hercules, and according to the scientists at the University of Texas, that was the first positively identified sibling to the Sun.
Yes, so there are a lot of other individual searches which are looking at, more smaller samples where they are targeting stars that have the similar properties to the Sun. So in terms of its temperature, its size, and similar compositions. So there is a bit of a distinction that has to be made between what is a solar sibling versus what we call a solar twin, if you like. So it's a twin. It's a bit of a difficult terminology. We think of twins as necessarily being, born together. But a solar twin in these terms is something that looks identical to our Sun, but not necessarily one that formed together. Does that make sense?
Yeah, but you're looking for siblings, aren't you? Stars which formed in the same molecular gas and dust cloud as what our Sun was formed in.
Exactly. So it may not necessarily have the exact same parameters as the Sun. So in other words, if you take a family, you'd have some which are older, some are younger. So it will have a similar chemical composition, but not necessarily the same temperature and size and so forth, because it's the chemistry that we are using as a tag to reconstruct these dispersed star clusters.
And that's where GALAR comes into the picture. It's taking spectroscopic signatures of all these stars.
That's right. So the spectrograph that we are using called Hermes, it was the latest instrument that was installed on the Anglo-Australian telescope. It's special because it's got what we call high resolution. And high resolution in this case means we are breaking up the starlight into finer bits of wavelength so we can get more detailed measurements on the individual chemical elements. And what makes it even more special is that it's coupled with the existing 2-degree field fiber positioner, where we can get spectra for almost 400 stars in one hit. So we're not looking at star by star. We can get, many objects in one go, which is why we could actually get this survey done in the time that we have.
So you're getting a nice three-dimensional look at these stars as well, where they are in relation to us, not just a two-dimensional position in the sky.
No, that's right. So we are getting their motion, we're getting how they are moving in the galaxy, and we are also getting an indication of the distance that they're at. But what's the highlight is that we are getting elemental abundances for 20-odd elements as well.
Is there a huge range of different elemental abundances within the population of stars in the Milky Way? Because the Milky Way sort of formed at one time, does that mean there's going to be less variation compared to stars in other galaxies? There
are variations, and we know that from small samples as well. It's not strictly true that the Milky Way all formed at the same time, because it depends on time scale, because we do have star formation happening at different places and at different times around the galaxy. And subsequently, they all get mixed in, which is the survey that we're sampling, which is what the survey is sampling right now. So because of this different localized star formation, we do see a variation in the chemical content. So in other words, especially if you add time into the picture, so stars that were older, that were formed from material which are more pristine, and less polluted by other star formation events will have less metal content. And depending on the type of supernovae, because supernovae are the ones that pollute the gas, the types of elements in the material, in the gaseous material, is different. So that gives rise to different amounts of different elements. So there's a range. So to answer your question, do we see a range? Yes, we do. And it depends on what types of, how the star formation happened. In other words, was it very violent, where you had very massive stars forming first, and then they would go supernovae, pollute their neighboring gas, and then have subsequent star-crossed stars forming from that polluted mass? Or was it more calmer, or you only had a few massive stars, less supernovae types going on, and then therefore the enrichment process didn't really take off? So you do see these variations. And also depends on the type of supernovae. So going into a bit of detail, so different types of supernovae produces different chemical elements into the interstellar medium. So if you have cases where the entire core has been disrupted or it's causing pollution, then you have these heavier elements forming, whereas lighter elements can be produced by just from stellar winds even, which pollute the gas. So all of these different physical processes give rise to the changes in the individual elemental abundances.
By looking at these subtleties, you can discern different populations of stars that were likely to have been formed out of the same molecular gas and dust clouds, and also at different epochs in the galaxy's existence. So this gives you a huge kaleidoscope to look through, and that's what this is all about. That's what Galar's trying to achieve. And then at the same time, you've now got access to a new European Space Agency data set coming from the massive Gaia mission.
Yes, that's right. So the Galar data is very much in addition to the Gaia data, because obviously Gaia is producing information on their distances, their motion for billions of stars, but for all of the stars that are in Galar, you will get this extra information. So it is adding on to the results that Gaia will give by giving out all this chemical elemental information as well. Before the Galar survey, the sample size back in 2013-14 was of the order of 700-800 stars, definitely less than 1,000 stars. So we've jumped many orders of magnitude with this survey to be able to get individual elemental abundances for hundreds and thousands of stars and eventually a million stars.
A huge jump in what you can do compared to what was being done before. Is that because improvements in the spectroscope, or different ways of gathering the data?
It's the availability of an instrument like Hermes, where you can get high resolution and multi-object at the same time.
That's Dr. Gayandi De Silva from the University of Sydney. And this is SpaceTime. I'm Stuart Gary. A new study shows the Large and Small Magellanic Clouds are forming new stars at an ever-increasingly rapid rate. This acceleration in stellar birth rates follows a lazy start lasting several billion years. The Large and Small Magellanic Clouds are two neighbouring galaxies circling the Milky Way, located between 167,000 and 200,000 light-years distant. This increase in star formation rates in the clouds was detected by astronomers using the Sloan Digital Sky Survey, as they were undertaking the first detailed chemical surveys of galaxies beyond our own. The study's lead author, Professor David Nedeva from Montana State University, says these maps will help astronomers reconstruct the history of how these galaxies formed. The team are mapping the positions, movements and chemical compositions of thousands of stars in these nearby galaxies. The Large and Small Magellanic Clouds are named after the explorer Ferdinand Magellan, who led the first expedition to circumnavigate the globe, and who were the first Europeans to see the two satellite galaxies. The galaxies are only visible from the southern hemisphere, where they look like very bright, wispy clouds. As we mentioned in our previous story, Earth dwarf galaxies are currently undergoing gravitational tidal streaming of their stars and gas into the Milky Way. This galactic cannibalization is expected to continue until eventually both galaxies are merged into the Milky Way. Although humans have been looking at the Magellanic Clouds for millennia, this is the first time astronomers have been able to make detailed maps of the chemical composition of the stars within them. And once again, the key to making these maps was collecting the spectra of as many stars as possible. To undertake this task, the authors used the Apogee 2 South spectrograph on the Sloan Digital Sky Surveys telescope at the Las Campanas Observatory in Chile. Apogee 2 works primarily at infrared wavelengths, longer than the human eye can see. Measuring the detailed chemical abundances in stars can provide both a clock and a speedometer for star formation because of how the elements are created. The hydrogen came from the Big Bang, as did most of the helium. But most of the heavier elements, those which astronomers refer to as metals, were formed deep inside stars and only get released at the end of a star's life, often through supernova explosions. So, by adding up all the heavier than helium elements astronomers can see in all the stars in a galaxy, the total provides a measure of how many stars that galaxy has formed during its life. Meanwhile, the composition of the stars reveals the makeup of the gas cloud from which they were formed, serving as a clock for the recording of stars' ages. You see, stars make different elements depending on their mass. More massive stars make and release extra amounts of so-called alpha elements, things like carbon, oxygen, neon and magnesium. Early on in a galaxy's history, stars add a lot of these alpha elements to the galaxy. But as time passes, the rate of these alpha elements gets balanced out by other elements made by smaller mass stars. That is, unless a new burst of star formation occurs, throwing the balance off again. So, with a clock of all the heavy elements and the speedometer of the alpha elements, astronomers can make detailed models to reconstruct the rate of star formation throughout a galaxy's history. The results show that both the Large and Small Magellanic Clouds have had histories very different to that of the Milky Way. Their stars' relative abundances of alpha elements came into balance at a much lower value of heavy elements, in other words, earlier times than for the Milky Way. This indicates a slow rate of star formation during the galaxy's first few billion years of existence. But very recently, during the past 2 billion years or so, alpha elements have become more plentiful, indicating a burst of recent star formation. Astronomers think this is due to the interaction of the Magellanic Clouds with one another as they both tumble towards the Milky Way. Over the next few billion years, both Magellanic Clouds will continue to merge with the Milky Way, as the gravitational force of our much larger galaxy pulls them in. As a result of this, the cloud's rate of star formation should increase to even greater levels than what they are now. You may recall in last week's show, we reported that in about 2.5 billion years from now, the Large Magellanic Cloud is expected to be completely consumed by the Milky Way, in the process triggering a cosmic explosion of star formation known as starburst. I'm Stuart Gary. This is SpaceTime. The United States is warning Iran against another planned test of a nuclear-capable intercontinental ballistic missile. However, new satellite images suggest preparations for such a launch are continuing at the top-secret Imam Khomeini missile site. The images show a large white container, thought to be carrying a small missile first stage, arriving at the launch pad's vehicle assembly building on January the 4th. Iran's Deputy Defense Minister then claimed that Tehran will launch 3 satellites into space shortly. In response, the US Secretary of State Mike Pompeo has issued a preemptive warning to Tehran that America will not stand by and watch the Iranian regime's destructive policies place international stability and security at risk. Pompeo says such rocket launches would violate United Nations Security Council Resolution 2231, which endorsed the 2015 nuclear deal between Iran and world powers, calling on Iran to refrain and not undertake activities including launches related to ballistic missiles capable of delivering nuclear weapons. Iran has already undertaken numerous long-range missile tests under the guise of space launches. In July 2017, Iran launched a Simor ICBM in an act which the US State Department described as provocative. Then in December, Washington slammed Tehran for launching a medium-range ballistic missile, which Pompeo says was designed to carry multiple warheads. That launch followed US President Donald Trump's decision back in May to pull out of the Iran nuclear deal, citing multiple violations by Tehran, including its sponsorship of terrorist organizations such as Hezbollah and Hamas, and intelligence evidence suggesting it's continuing to secretly develop thermonuclear weapons. However, the oil-rich nation has rejected these allegations, insisting its nuclear program is for peaceful power generation only. The Islamic Republic's missile technology is closely based on banned North Korean missile technology, which itself is based on Chinese and early Soviet Union launch vehicles. The United States, the European Union, and many Middle Eastern nations fear that, just like North Korea, Tehran is using its space program simply as a cover to develop ballistic missile nuclear weapon delivery systems. That system is now in place for Pyongyang, which has also tested and miniaturized thermonuclear warheads to fit on those missiles. Analysts within the intelligence community say there are now real concerns that Tehran is following North Korea's lead, with Iran's own missile and nuclear weapons programs accelerating. The Seymour or Phoenix ICBM is a 27-metre tall two-stage missile capable of carrying a 350-kilogram payload into orbit and 1.2 tons on a ballistic trajectory. Also known as the Shafir-2, the Seymour uses a North Korean-developed first stage called the Yunar, which is equipped with 4 Scud missile rocket motors. The Seymour's upper stage uses the Safar missile, which is simply a modified Shahab-3 medium-range ballistic missile with the warhead removed to make room for a satellite payload. The Shahab-3 can deliver either a 1,200-kilogram warhead or 5 MIRV or independently targetable multiple re-entry vehicle warheads over a range of 2,000 kilometers. In fact, the International Atomic Energy Agency says that in the early 2000s, the Islamic Republic may have explored various fusing, aiming and firing systems to make the Shahab-3 more capable of reliably delivering a nuclear warhead. The Shahab-3 is based on North Korea's Nodong-1 missile, which was developed using Soviet-sourced Egyptian Scud-B missiles and Chinese-sourced Scud-C missile technology. As for the 3 satellites planned for this launch, they include the Dowsey, Payam and Nahib-1 mini-satellites. Interestingly, all 3 are equipped with satellite imagery capabilities, allowing Iran to keep an eye on their enemies. The Dowsey is a 52-kilogram Earth observation microsatellite, which will orbit the planet at altitudes of between 250 and 310 kilometers. The Payam is a 90-kilogram Earth observation satellite that will keep an eye on what's happening below from a 500-kilometer high orbit. As well as having satellite imagery capabilities, the Nahib-1 will also carry a Ku-band communications package and be placed into a geosynchronous orbit. This is Space Time. I'm Stuart Gary. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. The Weather Bureau says 2018 was Australia's 3rd warmest year on record. The official figures show that last year was on average 1.14 degrees Celsius hotter than the national average between 1961 and 1990. The new figures mean the 11-year mean average for 2008 through to 2018 was the highest on record at 0.77 degrees Celsius above average. The new data means that only one of Australia's warmest 10 years occurred before 2005, and 9 of the last 10 years have been warmer than average. The Bureau says warming associated with anthropogenic climate change has seen Australia's average mean temperatures increase by just over 1 degree since 1910, with most of this warming occurring since 1950. The Bureau also found the Indian Ocean exerted a strong influence on Australia's climate during 2018, with dry conditions associated with a positive phase of the Indian Ocean dipole. The tropical Pacific Ocean had less of an influence, starting the year with a very weak La Niña, which decayed during February and had little if any impact on Australia's rainfall. It then moved into neutral conditions, and while there were signs of a potential developing El Niño from late July, conditions failed to progress to a fully fledged event by year's end. 2018 also provided above-average temperatures for nearly all states, and it was the warmest year on record for New South Wales. Meanwhile, the average annual rainfall for 2018 was 412.8 millimetres, 11% below the 1961 to 1990 average of 465.2 millimetres. Scientists say the mass die-off of millions of fish in Australia's Darling River system was caused not by drought but by bad water management and irrigation farming. Officials initially tried to blame drought and rapid shifts in water temperature disrupting algal blooms. But Professor John Williams from the Australian National University says dead fish and dying rivers happen because people are extracting too much water from rivers. He says the current tragedy was predicted and is therefore no surprise. Williams points out that many of the millions of large fish which are dying have lived for more than 50 years through many equally severe droughts. Clearly, current management plans have failed. A new study has found that baby boomers are hitting the booze at dangerous levels. A report in the Medical Journal of Australia claims more older Australians are drinking at risky levels as the baby boomer generation ages. Researchers say that while the percentage increase is small, it means an extra 400,000 people over 50 are now drinking at potentially problematic levels. Between 2004 and 2016, the proportion of risky drinkers increased from 13.4 to 13.5%, and the proportion of high-risk drinkers increased from 2.1 to 3.1%. A new study has shown that people who believe in conspiracy theories such as aliens walking amongst us and the Apollo moon landings being a hoax are far more likely to fall for fake news. The findings, reported in the Australian Journal of Psychology, also found that a person's political beliefs are consistently good predictors for the likelihood of believing fake news that supports those beliefs. The study suggests that a conspiratorial worldview and a schizotypal personality are also good predictors of a person's likelihood to be taken in by fake news stories. You're listening to Space Time. I'm Stuart Gary, and that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through Apple Podcast iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, from SpaceTimeWithStuartGary.com, or from your favorite podcast download provider. SpaceTime's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., and available around the world on TuneIn Radio. If you want more SpaceTime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us on Twitter through @StuartGary, at Spacetime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. This has been another quality podcast production from Bytes.com.